Pleasure to welcome Fabio Cuzzolin, Professor of Artificial Intelligence at Oxford Brookes University, and we're talking epistemic AI. Hi Fabio, how are you?
Hi, thank you. How about yourself?
Yeah, very good, very good. It's always a pleasure to introduce a guest who has probably forgotten more about the subject of AI than most people know in the first place. So the virtual floor is all yours, and I'll come to you with any questions from our audience at the end.
All right, thank you. So today I'd like to talk to you about our Epistemic AI project, which is a Horizon 2020 FET project in collaboration with KU Leuven in Belgium and TU Delft in Netherlands. This is our website over here. This is a project with a budget of 3 million euros and duration 5 years, and its objective is to reimagine AI through a proper treatment of the uncertainty that stems from our partial knowledge of the world. After noting that current AI, despite its success, is still unable to deal with the kind of uncertainty that derives from lack of data, which severely limits its development. So we came up with this concept, which is sort of depicted in these figures. On the left, you see the way traditional machine learning learns from the available limited data. So usually learns a single model represented by the red dot with limited generalization power, so power of adapting to new types of data and domain. Whereas epistemic AI on the right starts from a stance of complete ignorance about what the correct model is, and then it just tempers this ignorance by using the available training data to learn sets of models compatible with the training data. So this is a new learning paradigm that we call epistemic learning, which seeks to learn models, to model how uncertain we are about the sets of models that are compatible with the training data that is actually available. And mathematically, this is done using a technique from second-order uncertainty theory, which I'm going to explain in the next slide. So not a lot of people know that probability theory is not the only mathematical theory of uncertainty. And in fact, there have been a number of formalisms proposed over the years to extend or replace classical probability. And two of them are depicted here on the right. So on the top, you have creedal sets, which are convex sets of probability distributions, for instance, in blue. And at the bottom, you have random sets, which are set value random variables, represented by this clocked eye at the bottom. With these are standard random variables, they only output sets of possible outcomes with certain probabilities at the end. So what we're doing in this project, we are leveraging these advanced mathematical tools, like creedal sets and random sets, to produce new types of AI models and learning procedures. Again, this is a representation of the concept of epistemic learning. So on the left, you have traditional machine learning. You use the training set to learn a model in red, and then you use this model to make a prediction, like a single prediction usually, on the space of possible distributions in the target space, for instance, the set of classes. On the right, you have epistemic learning, which learns a constraint or epistemic model on what the correct model is, and then uses this epistemic model to produce an epistemic prediction, for instance, in the form of a creedal set, like I explained. So in the following, I'm going to explain a couple of the 2 or 3 of the models that we produced recently as part of this project. We started from the very foundational machine learning, which is statistical learning theory. Statistical learning theory aims to derive bounds on how much the future loss of a machine learning model is going to be on new unseen data. For instance, these expressions have this form: the probability of the loss of the model on future data being very different, greater than epsilon from the loss on the training data is smaller than delta. So if these bounds are tight, we have some assurance on the model's future performance. However, these bounds are derived under the assumption that the probability distribution that generates the test data is the same as the probability distribution that generates the training data, which is a very unrealistic assumption. For in any real-world scenario, the data after deployment can and will be very different from the training data. So can we make those bounds more realistic by relaxing this assumption? This is the purpose of this work called creedal learning theory. So if we assume that instead of having a single training set, we have a series, a sample of training sets collected under different conditions or generated by different data distributions, then we can learn a creedal set of possible, like a convex set of possible data generating probability distributions depicted here. And then using this creedal set, we can derive generalization bounds on the future performance of the model under creedal uncertainty, which is represented by this formula here. These have the same analytical form as traditional bounds under statistical learning theory. This work has been recently published at the top conference in machine learning, NeurIPS 2024. Another example of our work is in classification. It's a new concept called random set neural network. In classification, a neural network has to predict, for instance, the class an input belongs to. What we did is designing and testing a new class of neural networks able to model this epistemic learning using the theory of random sets, and we called it random set neural network. So the network differs from the traditional one only at the end, the output layer, because the output layer outputs a score, which can be normalized to a probability for each possible sets of classes. Obviously, you cannot do that for all sets of classes, so we do efficient budgeting to derive what the truly relevant sets are for a given training set, and then we output scores for just those. And also we designed a suitable loss function for the training of this random set neural network. This is work under review at another top machine learning conference called ICLR, or ICLR. This is the architecture of random set neural network, which is very technical, but the only important bit is this one. So you have new types of output layers at the end of the network, the output scores for the relevant sets of classes, and then you're going to have a prediction in the form of a creedal set, like we've seen before. You can also compute a central prediction for this creedal set called the picnistic prediction, and compute accuracy of the model in the usual way. The interesting bit is that when you evaluate this compared to all the other recent baselines, traditional neural network based on neural networks from ensembles, we have better, this is us at the bottom in bold, we have better accuracy and same the inference time as standard NNs, but also we have better ability to identify when your data points are out of distribution, so they're unusual or rare, very different from the training data. We have better robustness, increased robustness to adversarial attacks, and we also have statistical guarantees by using conformal learning on top of random set neural network prediction. So you can see here we are better than all our competitors, evidential neural networks, Bayesian neural networks, and standard CNNs. Another model that we recently published at NeurIPS 2024 in collaboration with Karel Leuven in Belgium is called Deep Ensembles of Creedal Networks. And here the idea is to produce ensembles, not of traditional networks, but of networks that produce creedal set predictions as depicted here in different colors. Then the ensemble aggregates all these creedal predictions from the members of the ensemble into a single creedal set, and evaluation can happen in the usual way. And when you evaluate this, as shown in this table, we demonstrate better accuracy and lower calibration error, which is a metric of how well the neural network scores correspond to the number of times the network is correct, compared to conventional ensembles. So here you can see in bold, we are better than standard ensembles of deep neural networks across the board on different data sets. These are standard data sets used in machine learning like Cypher10, Cypher100, and ImageNet. We also have a better ability to detect out-of-distribution data over several data sets. Again, our measures of out-of-distribution detection is better than our baselines. We also importantly propose a new framework for evaluating epistemic predictions or predictions under uncertainty, because At the moment, even neural networks with uncertainty are evaluated in a traditional way using metrics such as accuracy, precision, and recall. So we did in work that is currently under review at AI Stats 25, is proposing a new unified evaluation framework for evaluating all sorts of types of uncertainty-aware predictions. So like you can see standard neural networks that produce single predictions in a space of possible classes. You have Bayesian neural networks that produce a cloud of such prediction that can be mapped to a credo set. You have ensembles, you have credo predictions, you have random set predictions. So all these different types of uncertainty-aware prediction can be evaluated in the same way using the same metric, which is explained here below. And that allows us to do model selection, so to select the best model with the best trade-off between precision and accuracy in real-world scenarios. Finally, I want to talk to you about how this principle of epistemic learning can be extended to generative AI, which is the topic of this event. And we are working to do this in two different contexts. One is diffusion models. Many of you will be familiar with DALI type models that can generate photorealistic images. The way these or open or like diffusion models, the way these diffusion models work is by learning a reverse denoising process. So they start from they learn how to start from a random noise picture and gradually get back to a real image, like in this example. This process can be learned by a neural network, and that is what allows AI to generate like photorealistic images like this one. The problem, even with state-of-the-art current diffusion models, though, is that is depicted in this picture. So, for instance, if you ask them to draw like an oil painting of a horse sitting in an airplane, Stable Diffusion will produce samples that are very similar in style, like here. If you prompt them to create a picture of a girl eating a dinner, it will deliver girls of similar age, hairstyle, and skin complexion. At the bottom, if you just replace girl with female, you get basically the same scenes with just an older woman instead of a girl. So the problem is variability of the outputs. So diffusion models, even the best diffusion models, are not very diverse in the terms of the outputs they produce. So what we thought of doing was using second-order uncertainty theory to model the probability distribution of the Gaussian noises themselves. If you do that using like what's technically called a normal, an inverse, normal inverse gamma distribution like this, what you have more variability because you can control the different noise levels that you use at each of the stages in the process. And as a result, hopefully we're trying to demonstrate you have better variability in the images that are generated. The other thing that they are working on at the moment, this is also under review at AI Stats, is large language models based on random set predictions. Again, large language models are very successful, but they suffer from the inability to understand the differentiate false from true, or hallucination, as it's called. So we are working on a random set large language model that predicts not the probability of the next token in a sentence, like traditional language model, but a random set distribution on the next token. And this hopefully will allow language models to reduce hallucination problems and understand the difference between true and false. What's next? And I'm concluding, if that's okay, with this one. So the work we've done so far demonstrates that epistemic learning works better than traditional AI, produces more robust predictions, more ability to adapt to new domains, ability to produce generative AI with more diversity and less hallucination problems. So what's next for us is, there are a lot of things one can do. We can move on from a traditional one-off learning setting to a continual learning one in which the model learns from continuous streams of data. You can formalize epistemic deep learning at a parameter level and in a prediction level. So learn a random set or a credo set on the parameter space of a neural network. We can extend the approach to detection networks in computer vision, for instance, for uncertainty-aware perception in autonomous driving. We can model uncertainty in graphs for seeing representations under uncertainty. But we also need to finalize, this is ongoing work, we need to finalize our approach to epistemic diffusion and epistemic large language models to foster the generation of more diverse data and a new form of generative AI, like I said. One can also apply the epistemic learning principle to neurosymbolic AI, which is a new part of AI that puts together the expressive power of deep neural networks with classical logic. And also, we are planning to extend the epistemic approach to a type of neural network called neural operator models, which can model system of partial differential equations for representing complex physical systems and have wide applicability to AI for science and engineering, for instance, the control of nuclear fusion plasma, which is one of the projects we are working on in collaboration with the UK Atomic Energy Authority, or the generation of causal explanations, for instance, for climate change prediction. This concludes my presentation, so I'll be happy to answer any questions you might have for today.
Yeah, like that to pieces and put it back together again like that. For you, you were coming to it at the end there with some of your points of the discussion about the future of this research and the applications. Let's get the crystal ball out. In 5 years' time, how much further do you feel this particular subject could have gone? Because it really feels like we're still only sort of scraping the surface of its potential.
We are. I mean, obviously, this sub depends on how much resources will be available to us in the future. You know, these big companies like OpenAI and Microsoft have these, and basements full of TPUs that you use for training these models. So I think once the proof of concept is completed, and we know that this type of approach performs better than traditional deep learning, then we can look for resources to scale this up. One of the things that I just done is putting in a European Innovation Council transition grant on incubating a startup, developing a product based on this epistemic learning approach for robust perception and domain adaptation of autonomous vehicles. But more can be done in other application domains, like for instance surgical robotics, something I've been working on, and AI for healthcare in general. But like I said, I think AI for science and climate change prediction can be really high impact application. We can attract a lot of interest for in the future and get the resources that we need to scale this up.
Absolutely, all about that scale. This is a subject we could talk about for hours. It's absolutely fascinating, but the insight you've given us over the last 20 minutes or so, absolutely fascinating. Thank you so much for your time and joining us here at Tech and AI Live Gen AI.
Thank you for having me.